when we design a mechanical component, we have to look into the various type of forces acting on the system as well as the condition under which the system is going to work. The main reason to make such a kind of consideration is that even the temperature change can cause some adverse effect on the material. So in that aspect, we have to understand what is the significance of these thermal stresses. Even without the application of load, stress will develop in a material, and thermal stress is an example for that. Thermal stress develops within a material just because of the temperature change. So in this session, we will discuss about the thermal stresses, the cause, the reason for the development of thermal stresses in a material, and how we can rectify all these issues. So if you move forward, you might have noted these gaps provided on various structures. In almost every big structures, there will be a gap provided at various locations. The first figure is the photograph of a bridge where you can see some rubber beadings have been provided in between the gaps. This is the gap provided on the road on the same bridge, and you can see the gap provided on the rails. What happens if we don't provide this gap? The answer is right above this, because you can see the straight line rail has deformed into some zigzag positions, orientation, just because of the thermal effects. So we will discuss why such kind of deformation has happened in the system and what are the precautionary measures that we can take to account such kind of issues. So before moving into the thermal stress, we have to understand the thermal expansion coefficient of metals. Generally, metals have high thermal expansion coefficient, which explains us the rate at which the material can expand when there is a temperature change. Higher the thermal expansion coefficient means higher will be the expansion for the unit change in the temperature. For example, every material will expand when we heat it up. That expansion will be of the very micro scale. We cannot even see it with the naked eyes. But as the structure becomes bigger and bigger, the amount of expansion will also be bigger and bigger. So that is being determined mainly by the thermal expansion coefficient. So thermal expansion coefficient is the property of a material which determines how much a metal can expand for the change in the temperature. Now, the unit of the thermal expansion coefficient is per degree centigrade. Usually it gives us the micrometer per centigrade. It is something like that. Now what happens? Kindly look at this figure. You can see that the gray colored portion indicates the actual metal, and when I heated it up, what happened? It elongated and occupied this particular position. So this is how it is going to expand. The expansion is happening in all the directions. Now we need to study about the thermal stresses. So this is just the thermal deformation happened on the material. And from now onwards, we are not considering the thermal expansion happening in all the direction. We are talking about the thermal expansion happening in the linear direction. So let us limit, or let us say that alpha is considered as the linear thermal expansion coefficient. That means straight line motion. That means we are not considering the elongation happening in all directions. Instead, we consider that the deformation has happened or the expansion has happened in the linear direction, like I have shown here. Now if we look here, we can say that if I multiply this alpha with the temperature gradient delta T or T, say T, what will happen? Degrees Celsius will get cancelled out, and the term which is left with is a dimensionless term, and this is called as the thermal strain. Alpha T is called as the thermal strain. So our temperature gradient multiplied with thermal expansion coefficient will give you the thermal strain. We know that strain is nothing but change in length upon original length. So if we want to find out what is a free expansion or linear expansion, how can we find it out? Simply cross multiplying the L to alpha T, and the answer we are going to get is alpha TL. So in simple words, we can say that for a material having thermal expansion coefficient alpha and length L, the free expansion is nothing but alpha TL. So this much the material is able to elongate for a change in temperature T. T is nothing but temperature gradient. For example, if a metal has subjected to an extreme thermal condition under which the temperature changed from 30 degree to 50 degree. So the delta is going to be 20 degrees. So that is called as a thermal gradient. Now here you have to understand clearly that if we allow this free expansion to happen in a material, that means if you are not restricting this free expansion, the material is free to expand. If we provide such a condition, there will not be any kind of stresses in the material. We know that there is no load right now in the system, but even without the load there can be stress, and if this particular free expansion is prevented, then the thermal stress will come into picture. That's a very important point you have to keep in the mind, because it is not something related with the normal load application. This concept is completely different. So when the free expansion is prevented, thermal stress is developed in the material. If we don't give any kind of restriction to this free expansion, there will not be any kind of stress even if there is a temperature change. If you consider the first figure, the thermal stress developed within this material is zero, absolutely zero. Even though there is a change in length, there is a strain, still the thermal stress developed in the first case is zero. Suppose if the same material is being taken from here, and if I place it between a rigid support and if I heat it, what will happen? Now this free expansion is completely arrested by this rigid support. There is no provision given for the expansion. In this case, definitely the stress is going to develop, and that is called as the thermal stress. And the value is nothing but strain into Young's modulus. The answer is alpha T. The equation doesn't resemble to any of the equation that we have learned till now. So this is a completely different entity and content. So understand clearly before you proceed. So the conclusion that we can make here is, if the free expansion is prevented, stress will develop, thermal stress will develop. Or one more conclusion that we can add to this is that the amount of thermal stresses developed within the material is proportional to the amount of constrained deformation, or how much we have restricted, that much amount of thermal stress will develop within the material. So now we have to see whether we have prevented the free expansion or not before we calculate the thermal stress. So that is the reason why we have provided the gap here. See, if a gap is provided here, when the temperature changes, this structure will expand and it will fill this gap, and the free expansion is allowed here. Since there is free expansion, there will not be any thermal stress. The structure will be intact. But in this case, there was no provision given for the free expansion, so the stresses developed within the material and it has deformed to the allowed spaces. And so such kind of gaps or cushioning materials are given in between the structures is just to permit the thermal expansion. Now if we move forward, we can say that thermal stress is purely depending upon the amount of restriction that we have offered in the system. Now what will happen if I move this support a bit? Right now I am going to change this support from this position to this one, and it will attain a new position like this. That means some amount of gap has been given here. So all these gaps can be considered like that. Some amount of gap is being provided here. Now a question will arise in your mind. So what will happen if this gap is completely filled by the structure? What will happen beyond that? I think by this time you know the answer for that. So till it reaches, or till the expansion clears the gap, there will not be any stress, and once it clears the gap and when this deformation is prevented, definitely thermal stress will come into action. So that is going to happen here. So when you heat this up, what will happen? This is going to elongate. This is elongate, it will elongate, and it will touch here. So till this condition there will not be any kind of thermal stress. The material is stress free, and right from the moment it touches the rigid support, thermal stress is going to develop. Now we have to, when we consider this kind of gap, it is stated as yielding. Supports yield means it is free to move a portion of delta. It is allowed to expand delta. That is the meaning of yielding. So right now the material has expanded and touched the rigid support. Thermal stress is 0, and from here onwards the stress is going to develop. And I have told you that we have to look into the constrained deformation. How much deformation has been prevented? If you want to know the amount of deformation that is prevented, definitely we have to look into the free expansion. What was the expansion that was supposed to happen for a temperature change T? Now let us consider that the material was supposed to elongate this much. This was the actual amount of expansion. That means if we consider from here to here, this is the total elongation, free elongation, and this is given by alpha TL. So alpha TL is the total elongation that is being allowed. If this alpha TL is less than delta, definitely there will not be the closing of gap and there will not be thermal stress. But if alpha TL is greater than delta, then the amount of constrained deformation, that means alpha TL minus delta, this much amount of expansion is being prevented from happening. That much amount of stress will develop, thermal stress will develop. So when we consider yielding is a very important phenomenon, because we provide yielding in almost all the structures, and we have to look for the safe condition. Definitely the linear expansion has to be lesser than the delta, or in other words we can say that we have to provide a higher value than the alpha TL as yielding. Then only this material will be thermal stress free. So this is going to be the constrained deformation. So amount of strain is nothing but constrained deformation divided by the original length. So if I say this much amount of portion is the constrained deformation, this is the constrained deformation, and this is nothing but alpha TL minus delta, this one. So alpha TL minus delta is the constrained deformation, divided by the initial length will give you the thermal strain, multiplying it with the Young's modulus will give you the thermal stress in a material when there is an yielding present. It's very important. Alpha TE is the equation for the thermal stress when the deformation is completely arrested, and if some amount of deformation is allowed, that is called as yielding. And if that is the case, definitely this is going to be the equation that we have to use while solving a problem. Now let us see the combinations in composite sections, how this thermal stress is going to work. Thermal stress, how it is going to affect the combinations, composite sections. You consider this as a material A and this is a material B. Let us consider this as material A and this is material B. both these have different thermal expansion coefficients. Let us consider that the alpha of A is greater than alpha of S, or let us say this is called as S, aluminum and steel. So the thermal expansion coefficient of aluminum is greater compared to that of steel. We are assuming like that. And we are interested to find out the stresses happening within the material. Here there is no support provided, the material is free, but they are sticked together. They are glued together or bolted together such that they will remain as a single system. Here we can say that the load, even though there is no external load, we can say that the load shared between these two are same. P1 equal to P2. You might be wondering from where this load has come into picture, that I will explain right now. See, now let us individually analyze the sessions. See, for a temperature change T, this aluminum was supposed to elongate this much and steel was supposed to elongate this much. This was the actual case, or it was supposed to be the way in which it has undergone a deformation. And I told you that this is glued together and they are remaining as a single system. That means right now the deformation is only this much. So they are remaining as a single system. If you look at this particular system, you can say that the aluminum was supposed to elongate much more when we compare the final state of the system, and steel was not supposed to elongate up to the final mark. This was the conclusion that we can make if we analyze the system separately. Now we have to understand how this has happened, why the deformation of aluminum was reduced and why the deformation of steel has increased. So in order to understand that, we have to analyze the system separately. So let us talk in terms of aluminum. So aluminum has a thermal expansion coefficient of alpha A, and as the temperature increases, this was supposed to elongate, right? So when it started to elongate, it is glued to the steel. The steel is not having that much ability to expand when we compare it with the aluminum. So what happens is that when aluminum tries to expand more, the steel will pull this aluminum backwards. The steel is going to pull this aluminum backwards. That means there will be a resistance that the steel is going to offer to aluminum for freely expanding, and that resistance is nothing but a load, or a mechanical load. In a physical sense, we can say that the steel is pulling back the aluminum from expanding. So that is the reason why I talked about the load. So aluminum is being pulled back by the steel, right? And that just because of that, the length of aluminum has not taken place up to the free expansion level. Now let us talk about, in the sense of the steel. What happens to steel? So if we consider steel, this was the case of steel, and when we consider the thermal expansion coefficient of steel, it was not having the ability to expand up to the level in which aluminum has gone. So when steel starts to expand, what aluminum does on steel is, aluminum start to pull this. The aluminum will encourage the steel to come a little more forward. It's going to pull. So because of this pulling from aluminum, what will happen is the steel will expand more than the free expansion limit. I hope you all got the concept. The higher expansion, thermal expansion coefficient material will be experiencing a backward pull, and thereby its length will not go up to the expected range, and the material with the which is having the lesser thermal expansion coefficient will experience a tensile pull, and thereby its length will go beyond the free expansion limit, and finally both of them will remain in the same position. This is how the equilibrium has happened. So right now we can conclude that the deformation happened on the steel as well as the aluminum is same, right? So that is the condition that we are going to provide it here. That means the deformation is same. dl of aluminum is equal to dl of steel. Now we have to build the equation for this condition, and the load that I have discussed here, P1 equal to P2, is the load that is being shown by the arrow. This has to be the same, then only they will be occupying the same position after the application of or after the temperature change. So now what are the factors that is going to contribute to this deformation, or what are the type of deformation that will be resulting here? We have two type of deformations here. One is because of the thermal expansion, and other one is because of this mechanical pulling or pushing. So we have to account this also. So whenever there is a mechanical pull, definitely we have to consider the previous equation that we have learned, sigma L by E. That is the deformation happening on a material when there is a mechanical pull. So what happens to aluminum? Let us talk about the aluminum, or let us talk about the steel first. The steel was supposed to elongate alpha TL here up to this range. It was supposed to elongate. This was the range. We'll mark it like this. So this was supposed to be the expansion range of steel, and this was nothing but alpha TL, this one. And because of the pull from this aluminum, steel increased its length again, and that is a mechanical pull, and that mechanical pull is being denoted by sigma L by E. So the net deformation of aluminum will carry a plus sign because of this tensile pull. The reverse is going to happen for the aluminum. Alpha TL was supposed to be the expansion of aluminum, but because of the reverse pulling or pulling back from steel resulted in a reduction of length deformation, which is nothing but sigma L by E. So this is going to be the equilibrium equation that we have to use. So solving these two equations will fetch you the value of thermal stresses sigma A and sigma S. Sigma A and sigma S are nothing but the thermal stresses happening on the steel as well as aluminum. So you have to look into the thermal expansion coefficient before you start to solve this question. So in this case one, you have to understand that the material is not arrested at any point. Still there is a thermal stress developing in the material. It is just because of the difference in the thermal expansion coefficient, and they are glued together, and because of that there is a push-pull effect happening within the material, and thereby the thermal stress is developed. Here there is no restriction provided, but still the deformation has not taken place. There is no external resistance, but because of the system property, a thermal stress has developed within the material. Now let us look into another case, case 2. If you look at the case 2, it's an interesting fact is that these two materials are held between a rigid wall. The deformation is completely arrested. The material A as well as material B will not undergo any kind of deformation. Whatever deformation happens, it is going to be within this length A plus length P, that's all. The rigid wall is not going to expand. So we can say that in this system what will happen again, when the material A is going to expand more, here it is given as S, instead of that you can write the letter as B. Okay, so for the time being let us write it as this is steel, say steel. So steel, this is the material steel. So when A tried to expand more, it is going to compress steel, and when the material steel is going to expand, it is also going to restrict A. That is happening here. So again the load is going to be the same, P1 is equal to P2. This is one equation, and we are supposed to find out sigma S and sigma A. This is sigma is thermal stress, sigma A is also the thermal stress in aluminium. Now what is the deformation happening here? Here there is no push-pull effect happening here. Definitely there is a compressive stress acting on the material. Tensile effect as well as the compressive effect is happening in the material. Here what we can say that since the complete thermal expansion is prevented, we can say that the prevented deformation is equal to free expansion. That means alpha TL of aluminium plus alpha TL of steel was supposed to happen within the system, and that particular deformation got arrested because of this rigid wall, and that much amount of pull will develop within the system, and because of that pull the deformation is listed as sigma L by E plus sigma L by E of steel. So the summation of the deformation happening due to the mechanical pull as well as because of the temperature rise has to be the same to maintain the system in equilibrium. That is what is happening in this case. So case 1 and case 2 are a completely different case. In the case 1 there was no rigid wall, some amount of expansion was happening in the material, but in the case 2 the deformation is completely arrested. If the deformation is completely arrested, this is how you have to solve the system. So upon solving this, you will get the value of sigma A and sigma S. This ST indicates thermal stress. This is also there is a correction here, so kindly make a note of that. This is not T, there is no T here. The T is absent here. This T I have given just to notate the thermal stresses, or in other words you can say that sigma ST is nothing but this one, and DL AT is this one. That's all. That's how you have to understand it. Okay, so this is the case 1 and case 2. There are different cases also. Even along with this material, these conditions, external loads also can come into picture. But to understand the thermal effect and how the composite sections will work, this is sufficient. So kindly go through these and try to understand what exactly happens within the material. And for details you can refer any of these textbooks. They have explained it very well, and you can contact me also, no issues. So this is how the material is going to develop, react to the temperature change. Thank you.